We project from this one as well. Just go to the thing and put on project on both screens. I'll display on both projectors. Can I press?
It's overheated. Alright. Hello everyone. Thank you for waiting. Welcome to the ELEC2133 crash course. I'm Jackson and I'll be running through the op-amps part of this crash course. Followed by me we have Anuka, Laith, Josh, Jashin and Otto, so it's a really big lineup. Trying to get you guys prepared for your finals. So what we'll be doing in this workshop is first we'll be going through some of the key content that will be covered in the finals. We'll be going through some questions, and then I'm not sure if you've done any past papers yet, but as a warning, the finals are very time pressured. So we're going to try and give you some tips, hopefully save you guys some time with just your working out. And yeah, so let's get started. So most of op-amps should hopefully be a recap of Quad 1 and your labs throughout the term. Just to go through some of the basics, we have our golden rules when we have negative feedback. Just to define negative feedback is when we have part of the input sampled to the negative output of your op-amp. So an easy way of recognizing that is identify a feedback network. Is it connected to the negative output? Bam, it's negative feedback. If it's connected to your positive output, obviously positive feedback. Cool. So when we have negative feedback, we have two golden rules. The first one being that the input voltages are at the same voltage, and the second one being that the input current into these nodes is 0. So we'll be using that for our analysis later on. With the rest of the slide, I've just listed some of the key configurations for op-amp amplifiers. I highly suggest, even though you might not like rote learning, these two, the non-inverting and inverting amplifier, are really good to save you guys some time in the analysis for questions. And we'll see that coming in handy when I do an example later on. Another key one is the inverting integrator, which we've seen in lab 3 to create the triangular wave from your Schmidt trigger. And your difference amplifier is also featured in lab 2. So these are all key configurations to keep in mind, and these formulas can help you save some time in the finals.
So will the slides be available after?
Yep, so if you guys want the slides later on, the slides will be available after. We can chuck up a link on the stream, and feel free to use that to help with your studies. Okay, moving on to ideal and non-ideal characteristics. Ideally, we expect these characteristics: infinite gain, infinite bandwidth, infinite common mode rejection ratio, infinite input resistance, and output resistance. Basically, when we move into the practical cases, we find that these are roughly true, but rather than being infinite and 0, they are finite numbers. So like really large gains, really large resistances, but our bandwidth is the main one that changes. Does anyone know why the bandwidth is so much smaller in a practical op-amp? Should be covered in your labs. Yeah, compensation capacitor. So with a practical op-amp, we have transistors and capacitors that make up our internal circuit. And what that introduces is parasitic poles, which cause instability at high frequencies. So we add in a compensation capacitor, which stabilizes the system, but also, unfortunately, reduces our bandwidth. All right. Most of these nonlinearities should be covered in your lab, so I won't go through them in too much detail. Saturation is very visible in the clipping of your output. Output current limit is also an effect of clipping, but rather than being from the voltage of your supplies, it's from the maximum output current that you can have coming out of your output voltage. So for example, for the LM741, if we have a limit of 20 milliamps, say we have 100 ohm resistance, then the maximum voltage we can get across that is going to be V equals IR, so that will be plus minus 2 volts. So that's just another way of clipping occurring through us hitting the maximum output current. Slew rate, again familiar from the labs, just the maximum rate of change of the output voltage. And then frequency response, as we discussed earlier, we need to introduce a dominant pole into our op-amps, which causes this single pole transfer function behavior, which we see here. So what we can see is a steady minus 20 decibels per decade drop-off. And this point here, again, familiar from your labs, is called the gain bandwidth product. So here, when we have a gain of 1 multiplied by our bandwidth, that defines our gain bandwidth product. But also, if you multiply the gain and the bandwidth at any point along this line, you should get the same value, because gain product bandwidth is constant. All right. DC imperfections is the most likely thing you'll be assessed on with op-amps in the final. So we have three main DC imperfections: bias current, input offset current, and input offset voltage. Likely you'll be asked, if you do get this question in the final, you'll be asked to find the maximum worst case offset voltage. And the way we're going to work towards getting that value is we're going to find each of these offsets individually, and then we're going to add up their contributions. One key note is that the absolute value around the currents is together, and that is because the input bias currents are dependent on each other. So we can't just take the absolute values of each of them and then sum them up. That'll give us an incorrect value. We need to consider them together. All right, so jumping into an example. Figure 1C shows a difference amplifier. The DC imperfections are as below. Assuming that the op-amp is ideal, from the above imperfections, find the worst case offset voltage. Cool. Where's Josh? Is there a way I can add an extra slide just to do working out?
Yeah, there should be.
Yeah?
There.
That one?
Yep. And just after, and you can do whatever type you want.
Cool. Alright, so let's start with the input offset voltage. So I'll redraw the circuit. So we have an op-amp, and we have an input offset voltage just at the positive terminal. Typically, conventionally, we put the input offset voltage at the positive terminal, and that comes before any of the resistances that we have attached. So we would have seen from the example that we have two resistors and then two resistors on the top. One key thing about doing this calculation is these input voltages will be grounded, because what we're using is superposition, and with superposition we're only considering one supply at a time. So these input voltages will be grounded, and we'll consider that in our sketch. So that's what I've done here. This is VN2, but it's grounded. And then same with VN1 is grounded as well. Great. So what I can immediately see is that these two resistors are connected in parallel. They're connected to the same node and they're both grounded. So I'm just going to draw them as one resistor. And I'm going to call this resistor R3 parallel R4. This one was R1 and this one was R2. So now I can see that since I'm assuming that everything else about this op-amp is ideal, that means that yes, these input voltages are going to be grounded, but also the current into this positive terminal is going to be zero, because we're assuming for this case that the bias current is zero. So if I know that the current going through this resistor and into the positive terminal is 0 amps, that means that I'm going to have a 0 voltage drop across this resistor, which means that this terminal here is actually also ground. Cool? So that means I can completely ignore this resistor. And now we see that this terminal here is simply going to be minus V input offset. Now this circuit should look quite familiar. Can anyone tell me what op-amp amplifier we have here? Inverting or non-inverting? Yeah, non-inverting. So I'm just going to use the formula for a non-inverting amplifier here. Rather than me doing the entire derivation, I can just use the formula. So the offset due to Vi0 is going to be 1 plus R2 on R1 times the positive terminal voltage, which is just negative Vi0. So this is going to be negative Vi0. Alright, let's try the next one. Does anyone have any questions about that first one?
Wait, why is it negative Vi0? Like, does it matter if you do negative Vi0 or positive Vi0?
It won't matter in the end, because if you look at the formula, we're taking the absolute value, right? But if you want to know the reason why it's negative, it's because the way that we've drawn this is it has a polarity this way. So the voltage drop is actually towards the positive terminal. So we're going to have a drop of Vi0. Yeah, all good. Okay, so now let's look at the input bias current for the positive terminal. So I'll redraw the circuit. And now we're assuming that there is a finite current going into the positive terminal. So again, these resistors are in parallel, so I'll just draw them in parallel. We have R3 parallel R4. So to find this resistance, to find this voltage, I can just use the resistance. Using Ohm's law, I can find that the positive terminal voltage is going to be a negative voltage again, because we have, so if I draw this correctly, we actually have the current going upwards, so the drop is going to be in this direction, so we're going to have a negative voltage at the positive terminal, and it's going to be negative R3 parallel R4 times IB plus. And then again, we have the non-inverting amplifier configuration. So I can just use the same formula. So the offset voltage due to IB plus is minus 1 plus R2 on R3, 1 plus R2 on R1, R3 parallel R4 times IB plus. Okay, and then our last one. So I might just use the same diagram to save time. Can everyone see that all right? Is this in the way? Is that better? Yeah.
Still see? Yeah.
Okay. Better? Okay. Cool. So now we're considering the input bias current into the negative terminal. And we're assuming that this is the only imperfection in our whole circuit. So that means that this current here in the positive terminal is again going to be 0 amps, which means that again for this resistor, we're going to have a 0 voltage drop. So I can redraw my circuit as simply a ground at my positive terminal. And now we just have to consider this branch here, which is connecting our input offset voltage to the IB plus. Another thing to consider is that because we have negative feedback, our golden rules are going to apply, and that means that the positive and negative input terminals are going to have the same voltage. So since we figured out that this voltage was ground, that means this voltage is also ground, and that means the voltage drop across this resistor here is going to be 0 volts. So again, this resistor doesn't actually matter. And we have ground here. One key point to make is that there is actually going to be no current flowing into the ground, because the ground that we've created here is a virtual ground from our golden rules. And all the current will be going into the negative terminal, which is IB minus. So since I know this is 0, then the current through here must be IB minus. So then I can I can write an equation. So since the current's flowing this way to ground, it's going to be a positive voltage. So we have the input offset, or the offset voltage of the output due to IB minus is going to be simply R2 times IB minus. Cool. Does anyone have any questions about any of the 3 derivations? All good? Cool. So lastly, we can use the formula for the total offset. So this is offset due to IB plus, which I can simplify right now actually. So this is minus 10 to the 6 IB plus, and this is going to be minus 101 VI naught, and the last one here is also going to be 10 to the 6 IB minus. So we have, in the first bracket, we have absolute value of contribution of IB minus. So 10 to the 6 IB minus, minus 10 to the 6 IB plus. And then we're adding on the offset due to the voltage. So that is just going to be minus 101 VI naught. So now looking at the values that I'm given, I'm not actually given IB plus and IB minus in this situation. So I'm going to have to use the IB and the I0 to get my values. If we look at the equations that we have, we know that the input offset current is just going to be IB plus minus IB minus. So we can actually use that to simplify this equation. So I can factor out the 10 to the 6. And this is simply IB minus minus IB plus. And this will just give me 10 to the 6 times I0 plus 101 V I0. And if we sub in the values from here, 50 nanoamps and 4 millivolts, we will get a final value of 0.454 volts. Cool. So this is just an example of how, if you know your non-inverting and inverting amplifiers, you can save a lot of time. Rather than doing all the derivations, you can really only write a couple of lines for each of the input offsets, and yeah, get your answer quite quickly. So that's all for op amps. I'll pass on to Anuka to cover nonlinear amplifiers. So it should be there.
Wait, how do I use this thing?
Yeah, I'll quickly.
Guys, my name is Anuka. I'll be covering nonlinear amplifiers. Just give us a second.
Okay. So you can like write this. Colors are all here.
Yeah.
To erase, you press this.
Okay.
If you need to copy anything, just show me you can do this.
Okay.
Tap it, and then duplicate, and then
What the? Alright, sure.
yeah.
Alright, how about like working out space?
Working out space, you go here, and you just go real wide, and then you just add some.
Could you
So
make
that's
that for me right now, like for the next
it. For these questions?
that question? The next is auto stuff.
Okay,
I'm not sure why it's there, but
so just that,
yeah,
and you start here.
yeah.
Okay.
Wait, hold on.
Do you need more working out?
There should be a simulation here. Picture results. Oh, did you guys download this?
Yeah. Is it very important? Okay. Yeah.
Okay, that's fine.
Might have
That's
to
fine.
leave it.
No, it's chill.
Alright, I'll leave this with you.
Yeah.
And this is the microphone.
Yes.
Okay, good luck.
Okay, so I just draw here. Alright. Alright. Hey guys. Hello. I'm gonna start on nonlinear amplifiers now. Are you guys ready? Yes, ready? Okay, cool. Okay, so basically up to about week 6 or 7 in the course, we had been covering, we'd been working with amplifiers with negative feedback. But then there's a point where we cover nonlinear amplifiers, which is basically amplifiers that have positive feedback, okay? Meaning, for example, this op amp here. If you have a positive, if you have a, give me a second. Okay, if you have a positive voltage over here, right? What will happen is the amplifier has positive feedback, which causes the voltage at the output to saturate to positive VCC, right? Why is that? Because the difference across the two terminals is positive, right? Pretty simple. And if you have a negative voltage here, then it'll saturate down to negative VCC, right? Okay. So that's the kind of foundation for how we're going to do these questions, nonlinear amplifiers. So I guess we'll just get started. Okay, does anyone have any questions about the question before we start? Just have a read of it quickly. I'll zoom in a bit. Okay. Okay, all right, let's just start. So the first question is, we have to consider the Schmidt trigger on its own, okay? Okay, I guess before I go on, let's actually have a look at the different components of this circuit. So this component is a Schmidt trigger. you should just know this, just memorize this. It's a Schmidt trigger. Okay, this is an integrator. So this was on the slides that Jackson covered before. Integrator. And then this component down here is a clamper. Okay, so it'll clamp the output voltage. Right. And we'll kind of go through each component individually and figure out how they work. Okay? So to start off with, we want to consider the Schmidt trigger by itself. Alright, so let's just draw out the circuit. Okay. So we've got the Schmidt trigger. The first thing I'll point out is that the output voltage of the entire amplifier is actually connected to the input of the Schmidt trigger. So we labeled the input of the Schmidt trigger as VO. Okay? That's not because it's the output, it's because it's the output of the amplifier and it comes back in, right? Okay? And then this is Vx. Okay, so we're asked to plot the characteristics of this Schmidt trigger. So what I said before was that if the difference between the positive and negative terminal is greater than 0, what happens? What happens to Vx? It goes to positive VCC. In this question, it's actually called VL, so we'll call it VL. And if the difference is negative, then we will see that Vx goes to negative VL, right? So the first thing we're going to do is we're actually going to figure out an expression for this V plus, right? So V minus, what is V minus? V minus is just ground, it's 0, right? What is V plus? Well, we need to figure that out. So the way that we do this is actually voltage divider and superposition. All right. So the first thing we do is consider this VO by itself and suppose that Vx is grounded. Okay. So just ignore Vx. So V plus due to VO is going to be R2 on R1 plus R2. This is just voltage divider, right? Times VO. And similarly, V plus due to Vx, well, we can figure that out by then ignoring VO and just considering Vx, right? Does everyone kind of see what I'm doing here? Is that okay? Okay, cool. And so that's going to be R1 on R1 plus R2. It's a bit different. It's a bit different from the previous one. Altogether, we have that V positive is R2 on R1 plus R2 times VO plus R1 on R1 plus R2 times Vx. Okay? All right. Now, how do we go about drawing out the Schmidt trigger hysteresis diagram? Well, what we have to notice is that there are only two stable states for this system, right? The output of the op amp at Vx is either going to be positive VL or negative VL. It's not going to be anything else. So what we have to do is we have to assume that it's in one of these states. So let us say, let's assume that Vx is positive VL, right? Okay, well, if Vx is positive VL, remember what I said before, that the difference between the input and the output must be positive, okay? So I'm going to rewrite that here. So if this is true, then we have that V plus minus V minus is greater than 0, right? And what is V minus? It's just 0, so we can just cancel that out. Okay, we have an expression for V plus. That's R2 on R1 plus R2 times VO plus R1 on R1 plus R2 times Vx. But what is Vx? Anyone? VL, yeah, that's right. Because we assumed it here, right? That's why. Okay, and we know that this entire expression, which is just the same thing as v plus, is greater than 0, right? Okay, well we can just kind of solve this for VO, and we see that VO is greater than negative R1 on R2 times VL. Okay? Nice. Now what does this mean? Okay, it means that if Vx is VL, right, if it's positively saturated, then it will remain at this state as long as this condition is upheld. Okay? So we draw our input, which is VO. Okay, don't get confused by the VO, that's the input, right? And Vx, which is the output. So we're saying right now, our system is at VL, and it will continue to remain at VL until it crosses that threshold, which is negative R1 on R2 times VL. Okay? So it's like this. Any questions so far? Okay. Okay, well, we've assumed that we've looked at one stable state. However, there are two stable states. Okay, and I might just do this in orange. Okay. So we've done one stable state. We also have to now assume that Vx is negative VL, right? Okay. Well, what happens in this case? Well, if this is true, we have that the difference is negative. Okay. In other words, V plus minus V minus, where V minus is just 0, is smaller than 0. Okay, so we do the same thing. Substitute in V plus, which is R2 on R1 plus R2 times VO. And then we have the other one. Now, this one is meant to be times Vx, but Vx is now negative VL, right? So this is minus VL, and this is all less than 0. Okay, it's getting a bit cramped here, but is this okay with everyone? Okay, that's fine. So again, we can solve for VO. We can see that VO is less than R1 on R2 times VL, right? So then so basically, if Vx is equal to negative VL, right? It will continue to be at negative VL until it does not hold, until this condition is not upheld anymore, right? Yeah. Okay. So that's the very first part of this question. Okay, any questions before I go to the next part?
Just for the direction.
Yeah.
Do we normally just assume that, so let's say that now it's from negative, so it comes from negative to positive, so that's why arrows goes from left to right?
Yeah, for the direction, it's because you can kind of think of it like if you're over here, right? Like the only way that you'll cross this boundary here is if you go in this direction, right? Does that kind of make sense? Yeah. Okay, what's the next part? So we have to now show that the resulting waveform, well, we have to actually draw the three waveforms that are here. Okay, so let's first consider, how do I make a new page? Okay. Okay, let's first redraw this circuit. So we have R1, R2, R3, R4, capacitor, and then all of this is connected back to the output, to the input. Okay, now note that the switch is off, so we don't have anything here. Okay, so the question is asking us to draw the input-output, sorry, just the waveforms for Vx, Vo, and Vy. So Vx is here, Vy is here. Okay. So let's start with Vx. Everything okay? Okay, we'll start with Vx. So what we do is we first assume that it's at some state, okay? Let's assume that Vx is at positive VL, right? Because remember, Vx is the output of the Schmidt trigger that we just analyzed. Okay, it's one of two stable states. Okay, let's think about what actually happens in this circuit. So VL, like Vx is positive VL, it's a high voltage, or higher than 0, right? And on the other end of this chain of resistors is this node. And what is the voltage at this node if we assume that it's an ideal op amp? 0, right? Okay, so this is, we can just calculate the current that goes through here. Let's call it IC because it's actually going to be the same as the current going through the capacitor. So we can calculate that IC is VL on R3 plus R4, okay? Now, there's another expression for IC that we can use. IC is also the capacitance times the derivative of the voltage across the capacitor with respect to time. Right? This is VC. Okay. Well, we actually don't care about VC. We actually care about VO, right? So how do we figure out, like, what is the relationship between VO and VC? Which is minus VC. VO is minus VC. So, in other words, IC is also negative C times dVO dt, right? Okay, that's fine. What we're going to do is we're going to make these two equal. We're going to say VL on R3 plus R4 is equal to negative C times dVO dt, okay? And we'll come back to this equation, but for now, this is all we need. Okay, what you have to notice is that this VL on R3 plus R4 is completely constant, right? It's not changing at all, right? Same with C is constant. So since everything else is constant, we can say that the derivative of the voltage with respect to time is also constant, okay? That means that the voltage is increasing or decreasing linearly, okay? And why is that important? Because we can now plot VO and think about what happens. Okay, so VO will increase linearly, right? If it's actually, let's be a bit careful here. If the voltage is positive VL, right? Is the capacitor charging or discharging? It's charging, right? But what does that mean for the output voltage? It means that the output voltage is decreasing, right? Okay, any questions about this? Oh, did I try to draw it wrong? Hold on. Oh, yeah, thanks. Oops. Okay. Okay, so
Maybe that's why it's negative for the IC.
yeah. Okay. So the voltage at VO is actually going to be decreasing as the capacitor is charged, right? So we know that the voltage here is 0, okay? And we know that the voltage across the capacitor is increasing, right? It's getting bigger. Therefore, VO is getting more negative. It's becoming negative. So we start here, and it goes lower and lower and lower. And remember that VO is actually the input to the Schmidt trigger, okay? So since it's the input to the Schmidt trigger, we'll see that it'll hit that threshold value that we derived before, which is negative R1 on R2 times VL, right? And so what happens when it hits this value? What happens to Vx?
Vx goes to negative VL.
Vx goes to negative VL, right? Right? And then this capacitor will begin to discharge, causing the voltage to increase until it again hits that threshold value on the other side. And so on. So essentially at Vx we see a square wave with a certain period, and at Vo we see a triangle wave with a certain period as well. Okay, any questions?
What about Vy?
Sorry? Oh yeah, Vy, yeah. Okay, I'll get to that in a second. Yeah. Any other questions? Okay, cool. All right, now, okay, the question also asks us to find Vy. Well, it's quite simple because Vy is just a current voltage divider of VL, or of Vx rather. So it's Vx times R4 on R3 plus R4, right? So the waveform for Vy is going to be the exact same. It'll be the exact same, but multiplied by a constant factor. Okay. Cool. Question? Oh, okay. All right. The third question, and I see that the rest have been cut off. The third question asks us to find. Sorry. Can everyone see question 3? Okay. I don't know if you can see it, but okay, maybe I'll do this. Sorry. Okay, question 3. We want to obtain the expression for the frequency. Okay. How do we do that? Okay, the first thing to notice is that frequency. So we know we can kind of find the period using RC charging, which we'll get to in a second. But the thing I want you to keep in mind is that the frequency is 1 on t. So we can just find the period and then take the reciprocal, and we've answered the question. Okay. So let's go back to that expression that we derived before, which was that VL on R3 plus R4 equals negative C dVO dt. Hold on. Okay, so we have this expression which relates the voltage at the output to the voltage like VL, right? Okay, so let's actually just integrate both sides with respect to t. Okay. And we're going to integrate from time t equals 0 to the time it takes to charge it, so Tc. Now, what we have over here is kind of like a change of variables, so let's just cancel those out. It's a bit dubious what I'm doing, but we'll just do it. And we're going to integrate from the voltage at negative 0, at time t equals 0, which is going to be, well, what we're going to do is we're basically going to integrate across this path, right? we're going to integrate from this voltage to this voltage. So we're going to have negative R1 on R2 VL and positive R1 on R2 VL. Cool. Now remember, this is all just a constant, right? So this integral evaluates to VL on R3 plus R4 times TC, the time to charge. And it's equal to negative C times this one minus this one. Okay, and they're the same thing, so it's just negative, oops. So it's just, well actually positive, wait. Sorry, this one should be positive and this one should be negative because we are charging the capacitor, okay? Okay, negatives cancel out, the VLs cancel out. We can solve for TC, it's just 2C times R3 plus R4 times R1 on R2. And because our circuit is kind of symmetric, right? You'll notice that in the question, it's either positive VL or it's negative VL, right? The magnitude of the current is going to be the same in either case. So the rate at which the capacitor charges or discharges is the same, which means that the time to charge is the same as the time to discharge. Okay? Any questions? Does this make sense to everyone? Okay, good. I'll assume that it makes sense. So the total period, and okay, actually, before I move on, let's just actually highlight what I'm finding right now. So remember, this is when the capacitor is discharging, right? So TC is the time to charge. It's this length here. And then this is when the capacitor is discharging. Charging. Wait, yeah, this is when the capacitor is discharging, and this is when the capacitor is charging, yeah. So then the total period of this waveform is T, right, which is just the sum of the two. Okay, so that's what I'm finding. Okay, well, T is just the sum of these two, so T is 4C times R3 plus R4 times R1 on R2. And then the frequency is 1 over this, which is just R2 on R1 times 1 over 4C times R3 plus R4. Right? Okay, makes sense. So we've just found an expression for the frequency of the generated waveform. Now there is another question, but I can't see it because it's been cut off. So can I borrow someone's lathe, your laptop or something, Jackson? And I'll just copy the question down.
Is that overleaf?
It should, no, it's not on overleaf because I cut it off accidentally. Okay, give me 1 minute. Thank you.
Is it on the actual doc?
Sorry?
Is it on the updated overleaf doc?
Okay, it's on the doc, but you need to. Yeah, sure. All right. Okay. I believe it's
This one that hasn't been added yet.
Oh, okay, that's a bit. Let's ignore that. 0.55 maybe.
Sure.
Can you try that? Just check that it works. I don't know what happened, but it seems like the bottom question got cut off. Right. Can you?
So it should be.
Wait, that question.
This one?
Right at the bottom. Okay.
Didn't you just? Oh, you did the top one.
I'll just copy. Sorry.
Yeah, yeah.
I'll just copy it down.
Josh, are you still working on the overleaf doc? Do you want Otto to go next?
Just this. Maybe 15 minutes? 15 minutes? Maximum. Okay, guys. Hello. Are you guys ready to start again? Okay. So you can take that as your 5-minute break in the middle of the lecture. Okay. So the question is, we want to obtain an expression for the frequency of the VCO when S1 is on. Okay, what is the VCO? Well, this entire circuit is actually something called a voltage-controlled oscillator. Okay. So we have this control voltage, which is VC, and depending on this voltage, the waveform will change. Okay, so to analyze this, let's actually figure out how this component works, the voltage clamper, right? Okay, so I'm going to draw this part of the circuit. Okay. So the thing we need to recognize is that the diode, so first of all, to analyze this, we're going to assume that this diode is ideal. Okay? I'm going to denote this as V op for operational amplifier voltage. And I'll denote this as Vy because it is actually just Vy. Okay. Now consider what happens if, well, okay, let's consider this, right? V plus minus V minus is the difference at the input, right? And we know that V op is going to be some factor of this, right? So if V plus minus V minus is greater than 0, we can kind of assume that V op is going to be positive VL. And similarly, if V plus minus V minus is less than 0, we can assume that V op is negative VL, right? Okay. Now, what is V plus? Just VC. And V minus is kind of something we have to figure out. Okay. So consider what happens if, well, okay, actually V minus will just be will be Vy, assuming that this diode is open. Okay, so it's a bit weird, but let's actually just go through this one step at a time. You have minus, you have plus. So first, let's assume that this diode is open. Okay. What that means is we are assuming that V plus minus V minus is greater than 0, and that V op is positive VL. Okay. What this means is that the diode is reverse biased. There's no current flowing through it. You can treat it like an open circuit, right? Okay, that's fine. Then we can say that V plus is VC and V minus is Vy, right? There's nothing to say that V minus should not be Vy, right? Okay, so we can kind of substitute into this equation, into our constraints, and we see that Vc is greater than Vy. Or in other words, Vy is smaller than Vc. Okay. As long as Vy is smaller than Vc, our cutoff thing, our clamper, I'll call it, is gonna remain like this, and Vy is gonna remain as Vy. Okay. However, what happens if Vy is greater than Vc, right? If Vy is greater than Vc, in other words, if V plus minus V minus is smaller than 0, well, the output of the amplifier kind of goes down, right? It gets smaller. And you have some not small voltage on the input of the diode, right? So basically you'll have a voltage drop across the diode. Like basically the diode will be forward biased, right? There will be a current that flows through it. You can treat it like a short circuit. Like this. Now, notice that Vy is actually not from a voltage source or anything. It's actually a current division. Voltage division, sorry. So what we can say is that the voltage at the output, Vop, is going to get, well, since this is an amplifier with negative feedback, it's just going to become Vc, right? It's almost like Vy is getting overridden to Vc. Okay, so it's no longer that voltage division of Vx. It is now just Vc by itself. Okay, cool. We now have to go back and do the same analysis that we did before, but we have to now take into account that in the second case, or in the first case, where Vx is positive VL, Vy is something else, okay? So we'll get to what that something else is in a second. Okay, so far so good. Does everyone understand what's happening? Where is it? Okay, any questions? Not at all. You guys understand it perfectly? Okay, sure. Okay, so basically if Vx is positive VL, getting lost, sorry. If Vx is positive VL, then you can see that Vy will be kind of large, right? So if this happens, then Vy is going to get clamped to Vc. I'm just going to check my notes to check that I'm doing this correctly. Yep. And if Vx is negative VL, well, if Vx is negative VL, well, this voltage here is going to be negative, right? Which means that this is going to be positive, which means this is going to be a high voltage, right? Which means it's going to be an open circuit at the diode, which means that Vy will just be, as usual, the voltage division R4 on R3, the voltage division of X, right, Vx, right? So it's going to be voltage divided across here. Okay.
So is that Vc the voltage because the capacitor input voltage?
Oh, sorry, this is the control voltage.
The control voltage.
Yeah, yeah. So let me just go back to the thing. This one, yeah. Good question. Yeah. Okay. So then what we have to do now is derive our two charging equations again, or the periods. So there's Tc for T charging, which will be in the case that Vx is positive VL. And there's Td for discharging, which is in the case where Vx is negative VL. Okay? Now, TD, nothing has actually changed from the previous question, right? Because it's the same, like Vy is the same as it usually would be, right? So what can we say about TD? It's the same as before, right? And let me just find it so I can write it down. Okay, so TD is 2C times R3 plus R4 times R1 on R2, right? So that's chill, it's fine. Okay, TC is a bit different. So I'm gonna draw my circuit again, one more time. Everyone okay? Okay. Yep. Okay, let's do this again. Okay, so what we care about is the current going through the capacitor, IC, right? So now that we know that Vy is equal to positive Vc, where Vc, by the way, is the control voltage, not the capacitor voltage. So I'm actually going to call this C1 just to differentiate them. So Vy is the control voltage, right? Okay, what is IC then? Can anyone give me an expression for IC? Okay, that is one. Okay, let me just write that down. C dV C1 dt, right? The voltage across here. Yes, which is negative C dVO dt. Good. We also need another expression. Yes. Vy over R3, which is the same as, okay, I'll write this first, which is the same as Vc on R3, right? Okay, so we can just perform our solving as usual. I make them equal because they're both IC. And then we can integrate both sides from 0 to T charging. And here, it's going to be from positive R1 on R2 VL to negative R1 on R2 VL. So we can just integrate. Remember, this is all constant, right? This is not a variable. And then we have negative R1 on R2 times VL times 2. Okay, we solve for TC. It's going to be 2C times R3 times R1 on R2 times VL. Cool. Any questions? No questions? Okay. Okay, so TD, which is the discharging time, is 2C times R3 plus R4 times R1 on R2. Yeah.
VC over R3TC. The VC on the other side goes to.
Oh, did I miss? Hold on. Yes. Where did my VC go? Yeah. VL on VC. Wait, did I even write out the final expression? No, I didn't. Sorry. Okay, sorry, quick correction, TC. Yeah, so TC is 2C times R3 times R1 on R2 times VL on VC. And then that's it, yeah. Thank you. Okay, so what's the total time? It's TC plus TD, which is going to be 2C times, 2C R3 times R1 on R2 times VL on VC plus 2C R3 plus R4 times R1 on R2. And I'm again going to check my answers, just in case. That's times. Cool. Okay, and then for the final expression, give me a second. Okay. Then for the final expression, we say that the frequency is 1 over t, right? Frequency is 1 over t, which is going to be 1 over 2c r3 times, well, 2c times r3 r1 on r2 VL on VC plus R3 plus R4 times R1 on R2. So we can just cancel that. We can just factor that out. And this is going to be R2 on R1, like that. Okay. It was a bit messy, but does that make sense? I have a question.
Could you just, because you didn't go through the solution, could you just kind of like go through the answer again? Just make it clear.
Oh, yeah, good idea. So you want me to... Okay, you want me to go through the logic again, right? Okay, sure. So do you get the like charging and discharging? Is that fine? All right, cool. So which part specifically do you want to see, or just question? Okay. Wait, sorry.
When the diode add up in this system, that part.
When the diode adds up.
Yeah, this is just question 4.
Like back here, or sorry, I'm kind of back here, right? Okay. Cool. Let's go through this. So we can redraw the circuit quickly. So what we have here is Vy, right? So if Vx is VL, then Vy will be positive R4 on R3 plus R4 times VL, right? However, since like, okay, VL is going to be like 15 or something, right? So you can think of this as like some voltage. Let's just say that this is 6 volts or something, right? Well, what happens is we have 6 here. The difference here is, and let's just say that VC is 5, right? So the difference is going to be 5 minus 6 is negative 1, right? So then this voltage here gets pulled down to negative VL, right? And then this is 6 volts, and negative VL is like negative 15 volts, right? So you can see that the diode gets opened, right? Since it's opened, well, now we just have a voltage follower, right? So 6 volts gets pulled down to 5 volts. Is that okay? Does that kind of make sense? All right. Okay. I think that's it from my part. Cool. Yes. Who's going next? Otto.
Yeah, that's alright. I'll do it. Let's see what I can do with this. Yeah, could you quickly flash that QR code on there? So I think that's just you swap that cable and it should be good. And where is? Well, it's on.
While we're just waiting for the next section,
Yep.
if everyone could fill out the QR code just to mark attendance, thank you.
It would be fantastic. All right. How do I get back to the slides?
It should just be along. It should just
Okay,
that,
okay.
yeah.
That should be good.
And then if you want to add anything, I'll just add one for you. And then you just press that. And now that's in between.
Okay. All right. So we'll get back in maybe like a minute or two. I'm just gonna double check our online goers to see if they have any more questions, and we should be good. All right. That's rather strange.
Okay. Is it doing anything?
What? No. I mean, maybe just on the sources and
Wait,
stuff.
let's just try
like
just
get them
changing to-
reset.
Wait, let's just double click on it maybe.
Yeah, just hit quit settings.
Just check it. Yeah, there we go.
Where did I check the mouse? I checked the mouse over here. And
Oh, that's really small though. Wait,
yeah.
I might have to make it bigger.
Yes. Try and make it.
Oh, because I have to zoom out. Wait. There we go.
There we go.
I'll just do that and like that. That should be fun. There you
Alright, let's do this. Alright, let me just double check that online can hear us, and then we should be good to just jump back straight in. Yeah, online can hear? All right, perfect. So, welcome back. I'm Otto, and I'll be running you guys through DAC and ADC. Pretty much, we have two main questions. Fun fact, I made the second one over here. It's a very fun little count the nonlinear differences, whether it's an integral difference or a differential difference that we're looking at for error. And we have a very common DAC question from the past papers. You'll probably find this one in just about every single past paper. So let's go ahead and think of this one. So we have a ladder type DAC, as shown in this figure. Blocks are labeled SI to represent switches for different along different areas. And yeah, we want to determine what is V out given a certain switch position, which is given by a binary word, and certain resistor values and a reference voltage. All right, we ready? So, first things first, let's just cover the basic functionality of a DAC, particularly the ladder R2R ladder, okay? So, the essential functionality of this type of thing is we have this sequence of resistors, okay? And the very, very cool thing with them, and why it's also called a R2R ladder, is you have every top resistor is of value R, every down resistor is of value 2R, all right? And if we double check the diagram, that is so. Now, big thing with R2R ladder is equivalent resistances. Something to note is whenever a switch is turned off, this goes down to ground, and when a switch is turned on, it is just shorted straight to VREF, okay? This is the big thing that we need to be being very mindful of. So, if I jump back over to the other page, something we might note is, let's consider, I'm actually just going to tie it off with just 4, just for an example, okay? So we can understand some essentials. We know the first and last are always going to be grounded, all right? And never mind, this is going to be 3. Let's just do it with 3. Let's look at this first one, which we might call the most significant bit. This will be Sn-1, S0, and whatever's in between. So I'll just put this as Sn-2, and we won't think of the rest. All right. So for Sn-1, something very funky we have over here is because this is a very linear system, and we're only talking about resistors and turning on voltages, turning off voltages, we can just straight away apply superposition, okay? And the very important thing that I mentioned earlier is when the switch is off, this is just grounded. So let's go ahead and apply that just for our most significant bit, which is going to be Sn-1. So Sn-1, what kind of voltage does it supply? We know that VREF is over here, and the rest of these are going to be grounded. When we ground all of these, we get the very cool, what's a nice color? That's a nice color. We can pretty much section off every area going to the left somewhat sequentially and see a little pattern. So I noticed that these two R resistors simplify to a single R resistor. So I'll just say going this way, it's as though there's just R. If I look this way, 2 R's in series, I get 2R, R, 2R, and then I get to my first kind of more complicated area, because now I actually have the voltage to accommodate for. Are we holding steady so far just in the analysis? Any questions? All right, perfect. Let's keep it rolling. So now we're faced with a new circuit, which, I mean, it's not too riveting, but let's just hammer it out. Where this voltage is going to be V plus from Sn-1, okay? This is how I'm going to denote my superposition here, and we just need to determine that. We can consider this as just a very nice voltage divider of 2R over here, and these two resistors combining in parallel to give us R to ground, V plus from Sn minus 1 is going to equal to 1/3 of V ref. Okay? Good stuff. That's how we consider just the normal analysis of the most significant bit in a R2R ladder DAC. Now, that's fantastic. Now we have to do that n more times. Maybe not, maybe not. Let's consider now just the S minus 2, okay? We're only going to need to consider 2 of these because we end up with a very nice pattern. So let's go ahead and I'm going to redraw just a little bit. This is going for Sn minus 2. To R, dot, 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 oops. This one's going to be Sn minus 2, so this goes to V ref, and because we're just considering superposition, that's the only one that's on. We have one more R. This one goes to ground, because Sn minus 1 is considered off, and this one also goes to ground. This here is where V plus is. This is something else we might consider, but let's go ahead and take a peek. So, 2R, 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 and we should be good. All right. Now, understanding from previously, we know that looking left from over here, we end up with 2R on that side. Same working out as we saw previously. If we cut it just before the node, we get 2R. If we cut it just after the node, we get just R as the equivalent resistance looking to the left, okay? So if we run that back, we end up with another simplified circuit, all right? And we can also simplify this right section, okay? Just for the sake of an initial analysis. So, mind you, right-hand side goes to ground entirely, because this is a node going off to an op-amp. There's no current coming out of it, so we just consider voltage divisions. So let's do this once more. We have 2R going to ground. We have 2R going to V ref. And then we have, let's consider the equivalents, R to R. Just before the node, another 2R resistance going to ground. Now we did this exact same problem just previously, and that tells us that this voltage right here is going to be V ref on 3. But that's not the question just yet. That's voltage right about, I'm going to highlight this one, right about here at that node. So we need to do one final voltage division to get our V plus voltage. And I mean, if we kind of shortcut this, those two are in parallel, R is there, R in series with R, and I'm voltage dividing across it. I'm just halving the voltage, right? R, halfway through, half the voltage. So I end up with V plus from Sn minus 2 equals V ref on 3 times 1 on 2. And we contribute this all together with this little pattern of, okay, we always get this funky voltage division to get 1/3 of V ref, and then a consequent number of voltage halvings on the right-hand side of it. We end up with V plus from Sk, I'm going to use K, sure, equals V ref on 3 times 1 on 2 to a certain power. Now that certain power will depend on how far back we go. So if we're saying n minus 1 means that this has a power of 0, we can say n minus 1 minus k. All right? Fantastic. How do we put this in a closed form? Well, we can consider the voltage of the least significant bit. I'll actually run back to the question. If we can tell the voltage of this one, we know the voltage of this one contributed would be twice as much. So we kind of make a binary word, okay? So here we have a binary word given to us, 100100011. So let's go ahead and work that through, just to determine our voltage here. And then we have a non-inverting op-amp, which we covered previously. And we might come to realize that this resistor value actually doesn't really matter. Typically, it only matters when you consider the voltage offsets of the op-amp in this model. But yeah, all right, let's do this. So I believe we end up with, if I chuck this in, remember, most significant bit typically comes first. It's a little funky, so let's do that. We end up with 6 on 3, which is Vref on 3, gets multiplied by 2 to the minus, or rather, I'll just go 1 on 2 to the n minus 1. Or is it 2? Yeah, 1 on 2 to the n minus 1, and then chuck in binary 100100011, which, I mean, it's an 8-bit number. You could figure that out yourselves, but I mean, what are we thinking? Does anyone know what this is? 1, 2, 4, 8, 16, 32, 64, 128. Let's add these up. 147-ish gets divided by 128. All right, and that right there is this whole number. We multiply by 2. All right, and that is going to be V plus. Did we follow that? All right. So, any questions online? I'll just double check. All good. Fantastic. Okay. So that's V plus. Then we go ahead and we do the non-inverting op-amp. We know it's a 100K to 10K, and if we ever get in trouble and forget the formula, we can just recognize that, okay, same current going through, we know these two voltages are the same, and oh my gosh, same current through 10 times the resistance, just multiplies it by 10 to that point, so total, you get times 11, essentially, because there's 11 times the resistance for the same current. So then times 11, and that would give me my answer as V out. All right, any questions so far? Or is that nice and straightforward? All right, very cool, very cool. So, I mean, can everyone see that nicely? I think I crouched a little too far into the corner at some points in time, but all right, let's do this. That was a bit of the working, a little messy, and now we have ADC. So, very cool thing with ADCs, you probably find them in just about 3 more courses. They like to cover it again and again, just about quantization error and whatnot. I do believe I have a better question for this one, but you'll see these kinds of graphs. And really, it's just your analog minus your digital, and it gives you a nice graph on, okay, for what digital value does my analog input associate with, especially when I work with analog to digital converters. That's what it's all about. And that tells us about the differential nonlinear error and the integral nonlinear error. So I'm just going to go through a little bit of explanation because we're a little cut on time, and it's probably not the most relevant thing to cover for your finals because there's really not that many practice questions in history concerning it. But for the sake of completeness, let's go ahead and just talk about the concept. So, a differential nonlinear error is when we consider, okay, for analog input of 2, I got 2, but then let's consider what I got for 3. If I instead get for 3 something like this, where it's a half step instead of a full step, then I end up with a differential nonlinear error at step 3 of a minus 0.5, okay? Now that is regardless of where 2 was. So let's say 2 for some reason only gave us 1. So So for 2 only gave us 1, and then we got to 3 at some point, and we only went up still by a half. Then we still get the exact same differential nonlinear error of minus 0.5. Okay? Differential, it's just comparative to the last point. Okay? Whereas when we consider integral nonlinear error, let's go ahead and wipe this out to consider a new circumstance. Integral nonlinear error adds up the total error. So it's always with reference to your nice line of equivalence. So if I had 2 line up here and then 3 came over here, we still have minus 0.5 as our integral nonlinear error for 3, minus 0.5. However, if 2 instead was over here, we know that 2 is going to have an integral nonlinear error of minus 1. So I'll just put that as INL2. And if I get a half step over here for 3, I know the integral nonlinear error of 3 is going to equal to minus 1.5, right? Because it is 1.5 from where it is meant to be. It integrates the error. All right, good stuff. So for the sake of relevance, I believe we're gonna hop over to the next speaker. All right, who's up? All right. All good?
I'll just airdrop the new slides, that's it. Should just take a second. I might go through one example, because the first one's not too bad.
I mean, yeah, do this. You got this.
All right, give me a second. It's just the airdrop isn't coming on for whatever reason. I need the slides. No? Just do the theory? Yeah. I can't get the. Could you guys get the airdrop work? I'm trying to. See it's on? Yeah, it's on.
Okay.
Should be showing up, right?
Should. You might need to stop screen sharing just for a sec.
That might be it.
Yeah.
Okay, let's try that again. Ah,
Yep.
good point.
Good stuff. Right.
All right. I can do the first one if you want. If you don't want me to, I won't. It's just a BJT. Like I can show you. It's like very simple. But if you think it will be better if we don't
If
have
you
enough
think
time.
it's relevant, go for it.
It's a simple one. That's the thing.
That's fine.
Yeah.
That's fine. Yeah.
Okay, we'll go through it. All right. Everybody ready? Okay. Let's get to the meat of it. I'm going to introduce you back to transistors, everyone's favorite topic. I'm not going to go too in depth because I'm sure you guys have lots of practice with it, but we'll just have a quick review. So DC biasing and Q values should ring a bell. We're going to I'm going to show you how to solve for small signal parameters. And if we have time, we're kind of running out of time, we might get to this, okay? Let's see. First thing, I hope you guys have all seen this before. Basically, when you're dealing with the small signal model, there's 3 steps. You have to figure out, firstly, if you just have the DC sources, right? Where around would it operate, right? Because if you think about it, right, the AC sources are very small compared to the DC sources. So what you end up getting is a lot of what happens will depend on the DC sources. Next thing you do, you're going to solve for the small signal parameters. You guys have had a lot of practice with that, I hope. And finally, you can plug it into the RPi model. So let's get ahead. You guys should remember this. Don't worry too much about it. Most of your stuff is in forward active, right? But there are other ones, and you should know about them. Okay, you should have seen these equations before. Lovely equations. I love it when I have equations that mean I don't have to do like mesh or nodal or whatever. So that's great. It's basically free information at every point. So you guys should have seen this before. You have the base, you have IE, IC. Shouldn't be any news. Okay, so what I'm going to do is I'm going to solve this one. And I think I'll just do it on this slide. So this one is a pretty simple example. Do people feel comfortable with this example? I'm happy to skip it, or would you like me to go over it? Anyone got an opinion? Skip? Okay. Okay. Most of this stuff should be pretty comfortable to you. All this stuff, that's more current relations. Don't forget this one. It usually doesn't come up, but it is in the course content. That's the model at small frequencies. This would be another one. The basic idea, you would have figured out the I values previously. You would have used those, plugged it into the formulas here, and put it over here. Pretty simple. Yeah, we can skip over most of this. Similar stuff. Everyone's seen stuff like this before? Yep. Okay. I think most of this we should just be able to get through. You made my life really easy, guys. Wow, I get to go home. Here we go. Yeah, okay, that goes on to the next topic. Okay, are there any questions? I can talk a bit more about IC, whatever, intrinsic and extrinsic caps, but any questions at all? Yeah?
What's an intrinsic cap?
So it's a capacitor that's actually in the transistor versus outside the transistor. Extrinsic. Is that
Can you explain like the exponential equation?
Oh, the exponential one. Yeah, sure. Okay. So remember all those physics you guys ignored from first week? Or hopefully didn't ignore?
You go past it.
Yeah. You guys, here we go. So, wait, did I? Sorry.
Other way.
Is it back this way? Where did I put it?
Yeah.
There we go. Okay. So this one is just, it's actually kind of cool where you end up being able to derive. You notice how it doesn't really have much to do with the circuit. We have this thing VBE, right? Which is the voltage between the base and the emitter, divided by VT, which I'm sure you've all seen as 26 millivolts many times. We're able to derive the collector current. It's just a consequence of the physics. You won't see it in the exam. Is there anything you're curious about it, or?
Not really. I just like if we do get a question about it, what sort of questions?
It's very, very unlikely. Like, one thing they could ask is, like, what's the relationship of collector current to temperature? You can see that your threshold, VT, depends on temperature. So you can relate it that way, but again, I don't think it's going to come up in your final. So, yeah.
All right. I'll let you get onto that, Jashan.
Yeah.
Easy. You want to play black?
No, I'm happy to help with that.
Easy.
Yeah. All right. Can I have iPad plugged in and just on a blank?
Oh, you want on a blank?
Yeah.
I can make a new blank notebook if you want.
Yeah, go for that.
Okay.
Okay, we'll start off with. And are you able to take up the laptop? This one?
Yeah.
Yeah, easy. We'll sort it.
Easy peasy. Have fun with that.
All right. All right, guys. So you guys just got introduced to the parameters,
and now we're actually going to start doing some stuff with those parameters. So what I'm going to do is I'm going to derive 4 different types of amplified topologies for you guys. The idea behind this is that I want you guys to be able to go into exam, recognize a topology, and be able to apply gain equations, input resistance and output resistance equations, without having to create a small signal model that probably covers the entire page. Okay? So we'll begin with the common emitter. Okay? So let me quickly draw this out. Okay, this is pretty, well, funny it's in the name, but it's a pretty common topology. You'll see it come up pretty often. Gain equation is minus GMRC. Okay, it's very, very common result. And I'm going to go through how we're going to derive this now. Okay, so whenever we want to derive something like this, we're not sure. We'll just go straight into the small signal model. Okay, so we got B for here. I'm going to ignore R0 and I'm going to say that it's large enough for us to just ignore in our calculations. Okay? And since we're in small signal, this also goes to ground. Okay. Okay. Pretty sure you can just read this right off. V pi is V in, and then V out's just minus GM RC V in. Then we get the gain minus GMRC. Okay, so it's pretty nice. But what I'm going to do is I'm going to change this circuit a little bit. Oh wait, we're on GoodNotes. We can just copy it. All right. Now I'm going to add this resistor. So, does anyone want to take a guess to what this does? Does anyone know? So, this resistor over here, attached to the emitter, is called a degeneration resistor. It introduces negative feedback. You don't need to know exactly how it does that, but it stabilizes your gain. And also makes it a bit less independent on GM and more dependent on your circuit parameters. I'll go over feedback in a couple sections. Okay, so let's derive the gain equation for this. Oh, how do you add a new page on this? Is that it? There we go. Okay, so let's go into a small signal model. Move this down a little bit over here. Okay, let me quickly speed running drawing these circuits. Okay, so V out, the equation still looks the same, sort of. V out equals minus GM RC V pi. But what's different over here is that V pi is not V in. So we get Oh wait, that's not. It's not capital. Okay, so we end up getting this, but since we're gonna take the resistor over from the collector to the base side, sorry, the emitter to the base side, we're gonna add a 1 plus beta over here. Okay, sweet. Now, after some substitution, I'm not gonna include the exact working out, but we get Vn, oh no, we don't have, yeah, that's Vn over there. And then, let me just quickly take a look at the simplified version of this. Over, so this is going to be beta plus 1 plus beta Re. Oops, yeah. Okay, then we'll divide through by Gm. Sorry, this is supposed to be R pi. Okay, then we get equals 2. Then we get AV Yep. So that's your new gain equation over there. Okay. If you notice, this is less dependent on GM. Small changes in GM can arise to temperature. So it's good that Josh introduced you to that equation. If you remember, IB is IS times e to the power of VB on VT. So that means your certain parameters in your transistors are dependent on temperature, and this makes it less so, which is great. Okay, how are we looking on time? I'll move over to common base. Okay, so I'll just do common base. Yep, I'll see. We have V in over here. Okay, so common base has a low input impedance, so it's pretty good in that regard. Pretty sure this has a current gain, a unity current gain, about unity. Voltage gain is not different, is not unity, and we're going to derive that right now. So let's get into the small signal model for this. Okay, let me draw that on the other side. Okay, so we've got the small signal model over here, and what we see over here is that V pi is 0, so we can essentially zero this out, pretty sure. Actually, no, I'm going to redraw this. I'll redraw this into something a bit more like this. Vn and plus minus V pi. Yep. Then we get okay, let's quickly, we'll do some, I'll leave out the KCL equations over here, I feel like, because we're a bit struggling on time. So I'll leave that for the viewer to do, but essentially we get V out over V in is GMRC. Do you want me to stop now? You want me to? yeah, I'll let you go. I'll let you go now. So, yeah. So, we might include a document in the description. This will have derivations for gain, input and output resistance for all 6 topologies, as well as the generation for common source and common emitter. But yeah.
Can you explain why we're using that document?
Why
It's useful for the exam?
Useful for the exam. Okay. So if you had, which we might see in the crash course in a different question or in the exam, a 2-stage amplifier. Small signal model for that, like I said before, is pretty big, but you can turn it into 2, like it's 2-stage, right? So you can just find the gain for the first amplifier using the known equations and the input resistance of the second amplifier. And then you find the gain of that, the second amplifier, you can multiply those together, and you don't need to go into a small signal model, which probably will save you a lot of time in the exam. And that's why that doc's been made. So the idea is you read through the doc and you understand what's in it. Don't blindly follow the equations, because for some of the equations, let's go back to, okay, common emitter, right? If I added an RL over here, my gain changes to minus GM RC parallel RL. Okay, so don't blindly follow the doc, but it's a good starting point for understanding how these configurations work, what their gain is, what their input and output impedance is, and then you can make a decision on if you're maybe designing a circuit in the future. Okay, I want high input impedance, low output impedance. I can use a emitter follower for that. And it has unity gain as well. But yeah, so hope you found that useful. We'll move on to Leif now. So yeah. How much time do you reckon you take? 13 minutes. I'll be speedrunning, but I think I'll do that.
Okay, my turn. All right, wait, hold on. How do I do this? No.
So I don't know where your stuff is. It might be.
Why is there so many blank ones?
Oh, is it here?
Yeah.
This way? Where is it?
Which one? Near the end-ish. Oh, here, from there.
Here? Okay.
How do I make it?
And then if you just press this and then press that, you'll get a new one on this side, like in between the 2.
Okay.
Yeah. And have you used this before?
I can figure it out.
Rubber's there. Yeah.
Okay.
Okay. Yay.
All right, everyone. Now it's time to do frequency analysis. Okay. Now, this part of the course isn't too bad, but the problem is that a lot of the calculations are very, very tedious. You can think back to assignment 1, when you calculated your lower corner frequency and your upper corner frequency. For a 3-stage amplifier, you probably would have had to do like 6 times constant calculations for the first one and then 6 for the second one. So it's 12. It's quite a bit. You don't have that sort of luxury in the final. And so during my part, I'll try to teach you guys some intuition on how to take some shortcuts, because at least in this course, faster is better. So yeah, that's the main thing. And accuracy is a bit, it's a bit iffy. You don't have to worry too much about that, as long as it's within order of magnitude. Sure. All right, so the first part was just about input and output resistances. So this is just sort of piggybacking off of one of like the earlier like transistor amplifiers section. So hopefully you guys are a bit familiar with what I'm talking about here. What you can say is that for any sort of like system or circuit, you can sort of whittle it down into a black box where you've got some sort of input and then some processing in the middle and then an output. So many of your amplifier circuits, if you could imagine something like, this is some sort of amp, maybe a MOSFET amp. You've got some V out and then some V in. If you look from the input, you would get some sort of input resistance, and if you look from the output, you've got some output resistance. And for certain configurations, these would have different values. For MOSFET, generally you'd see really high input resistances and very low output resistances. Now, why? The reason for that is because if you want an efficient amplifier, you want to sort of maximize the efficiency of your signal sort of transferring through the system. So if you can imagine this is your first sort of black box amp, then if I, hold on, let me get my eraser. That's an eraser, right? There we go. So if I added amp 2, right? And now this is my V out. What I want to do is that I want the output from the amp 1 to be minimal so that most of the voltage goes straight into the second stage, right? Because this has a large voltage, has a large resistance. This one has a relatively low one, and then you do a voltage divider. So that's the general gist of why you get these sort of ratios. And so down here, I've sort of created a methodology on how you'd find R in and R out. So formally, if you remember from quad 1, it would be sort of attaching or turning off all of your independent sources, and then you'd add a dummy source between the terminals, and then you, if that was like a voltage source, for example, you'd send a current through, and then you take the ratio of Vx. So if you've got maybe RTH, you've got some dummy source Vx, and then you find the current going through it, and then you take the ratio, and that'll give you RTH. Does that sort of make sense? If you think back to quad 1, that was your method 3. So remember, method 1, method 2, method 3, and 3 always works. All right. Now, that works. There is, however, something that's pretty cool. You can follow this methodology, and it will work. But there is a quicker way, and that's just to sort of eyeball the solution. And the reason that you can eyeball it, at least for some of these circuits that I'll cover, is that we're working with hybrid pi models. And if I can draw one right now for you guys, what you'll see, it looks like, maybe I'll just actually, I'll add a, no. Yep, there we go. So if I drew this, no, that's collector, isn't it? There we are. No worries. This one is collector and this is emitter. So this is your hybrid pi model. What you can see is that there's sort of like a empty space here. A lot of the time this will be grounded. And so what that allows you to do is that when you do your circuit analysis, if you have some sort of transistor or some sort of amplifier, if you're looking at R in from here, we see that the second part doesn't really influence it. This part right here doesn't really influence it. And if you look from R out, the first part here doesn't really influence it. Now, this is pretty hand-wavy. I'll get into something that's more rigorous when I do an example, but that's the general gist. So when you're doing your exam, you don't want to have to like say, oh, I'm going to put a dummy source here, and then I'll calculate the current and whatever. Just eyeball it, and then you get the answer. So much faster. So that's that. Why am I rubbing this out? I don't need to. Was this it? No. Oh, there we are. Okay. Where is... Oh, there we go. All right. Now, short circuit time constants. How am I doing for time? Okay, all right. So, short circuit time constants. So, what we've found is that if you have some sort of system and you want to find the transfer function of it, right, you can graph maybe the gain of that system, so the ratio between V out and V in. And for some circuits, it might look something like, actually, let me add another one here. For some circuits, it might look like this. Some other circuits, it might look like this. Other ones, you would get sort of a plateau in the middle, and then you'd get 2 sort of cutoff frequencies, or 3 dB frequencies. Now, if I go back, there's an algorithm that Aaron's gone through, or that's in the lectures, that allows you to approximate your short circuit time constant. So this method allows you to find your lower cutoff frequency, FL. I'll go over the FH later on, but we'll start off with FL. Now, the reason why we have to follow this algorithm is that some of these transistor amplifiers are very, very complex. For a very simple circuit like this, if I drew this sort of circuit, oh, that's not good. And I'm measuring the output from there, and this is your input. Well, it's pretty easy to do a transfer function for this. What would this be? This would be this high frequency, then this would go to 0, so it would look like, is that about right? Yeah, it would look something like that. Now, I'll get to how I sort of just figured that out. There's a bit of intuition that you can build. But the main gist is that when you have a circuit that's got a lot of capacitors in them, you can't easily sort of eyeball these sort of things. You can't make a transfer function that's got something like V out on V in, and then some sort of complex of value function, or a rational function in the S domain. I keep pressing the wrong one. Here we are. Now, here's the algorithm. What it says is that if you pick from n external capacitors, these are your extrinsic capacitors. So going back to what Josh said, you'd pick one of the capacitors. You would measure the, what we would do is that you'd open circuit all your other capacitors that are also, you'd open circuit all the internal capacitors of your circuit. So these would be your capacitors that are inside of the models, so your C pi and your C mu. And then you would short circuit all the other external capacitors. I'll get to why you do that in a second. Now you calculate RTH across C1, call this R1, and then what you would do is repeating this for each of these capacitors that are on the external, right? Then you would calculate this. So it'd be the sum of the reciprocals of their time constants. This 2 pi normalization factor is just there because it's Hertz frequency, not radians. We don't have to worry about that. Now, I said here that the short circuit time constants are measured from the capacitors that are on the outside of your models. Now, why is that the case? Well, I've made a simple circuit here. Now, quick question. Based on just looking at this circuit, don't do any analysis, so no transfer functions. Can you tell me what sort of gain relationship this would have? Would this be sort of increasing and then it hit some sort of 3 dB point and then it would stay flat? Would it be at 3 dB and then it would go down, or would it be something like this? Option 1, 2, or 3? Does anyone have an idea? 3. Any idea why? Is there an intuitive answer?
It's a high pass connected to low pass.
That's a good way to think about it. One way you could really sort of find this, right, is just sort of doing casework. It's sort of basically what you said. What you would do is that looking at these capacitors, you just sort of consider low frequencies and high frequencies. So at low frequencies, what would happen is that these capacitors would be opened. So if this capacitor was opened, then what would happen is that there's no sort of signal that is going in to the output. So you can already imagine that the start of this graph would be increasing. And then when there is high frequencies, I mean, this would also be opened, but C2 doesn't really matter in that case. Then, if I considered high frequencies, this would be shorted, and this would be shorted. Well, what is V out over a shorted capacitor? Would that also be 0, right? And so you've got this sort of gray area in between where on one side they're both open, and on the other side they're both shorted. In each case, what you see is that they are sort of going to 0. So maybe you can intuitively think, oh, in the middle, it's probably not 0, somewhere in between, probably somewhere flat. And then there will be some frequency here, FL, and be some frequency here, FH. So that's how you can, for a simple circuit like this, you can sort of easily derive a transfer function, right? Just by sort of looking at the sort of properties that these capacitors hold, or where they are. Now, are there any questions so far before? Okay. Now, what's the big deal about these capacitors? Well, these two capacitors are sort of in two different configurations. This capacitor is a coupling capacitor. I hope you guys know what I mean by that. By coupling, it means you are getting rid of your DC frequencies. You might have done this in your assignment 1. I think there was probably one question that asked you what this sort of capacitor would do. This capacitor is your shunting capacitor. So at high frequencies, this capacitor becomes a short circuit, and then it sort of eliminates your frequency, or eliminates your signal at high frequencies. And those are the two things that you have to keep in mind. So coupling, these contribute to your FL, and shunting contribute to your FH. What am I doing? Okay, I should probably hurry up. All right, next slide. So, open circuit time constants. Now, we found something to give us. Actually, before I do that, I can probably talk a bit more about this. So, I was able to show you guys that this circuit, if I add another slide, that this circuit observed something like this. Right? This is FL. Now, I'm just going to tell you that this sort of idea generalizes to circuits that have a lot more capacitors, right? Because those capacitors can usually be sorted into two sort of categories. Your shunting ones, or actually, well, first you'd be your coupling ones, and then your shunting ones. And they have two different sort of purposes in the circuit. And so they would introduce poles at different places. Now, there is a result that you can derive if you do your single time constant circuit. So like the one I went through a bit earlier, it was, did I draw it? No, I didn't. I drew it, but I erased it. But it was this one. For these sorts of circuits, you can derive the result that the poles of your system are equal to 1 on RC, where RC is your time constant. So pole is equal to 1 on tau, which is equal to 1 on RC. Now, what does this mean? Well, that means that each of your capacitors are linked to a certain pole in your system. Now, this is going a bit into control theory, so I won't go into too much depth. But the idea is that you can sort of graph or put all of your capacitors somewhere on this graph. So this could be maybe pole 1, this is pole 2, maybe pole 3, pole 4, pole 5. And these are all dependent on their C values, which I'll go over in a sec. And so what our algorithm does to find FL is that it finds an upper bound for our lower cutoff frequency by calculating these poles. Because our equation here, which is essentially just going to be 1 on RC, R1, C1, 1 on R2C2 plus 1 on R3C3 and so on, this is just going to be equal to pole 1 plus pole 2 plus pole 3. So I probably shouldn't have done pole 3. If I made this pole 3 and then got rid of pole 3 here. So you're just adding up these poles right here, and then it would give you maybe some pole there that would be your upper bound. So you know that your gain, right, would cut off at most at that point. And then a dual idea would be these poles right here would give you the lower bound for your high frequency behavior. Now, why is that the case? Well, if I showed you the sort of equation for this, we know that, did I write F? This is not supposed to be FL, it's supposed to be FH. For FH, our equation is like this. 1 on RC plus RC1, RC2, RC3, whatever. Now, this might look like some sort of equation, right? But if I wrote this in a different way, maybe you might see some sort of thing you can liken it to. So this is going to be, if I did 1 on RC, 1, plus 1 on R2C2. So I've just sort of taken the double reciprocal of these. 1 on that. These 1 on RCs, right, I can just call them the R poles, right? The same definition I used before. 1 on pole 1, 1 on pole 2, plus 1 on pole 3. Does this sort of, this equation look familiar to any of you guys? Have you seen this somewhere when you're simplifying resistor networks, potentially? They're all in parallel. That's what I'm trying to say. P1 is in parallel with P2, is parallel with P3. And what happens when you do, if you think about your resistors, so it's sort of like an analogous problem, if you take your resistors in parallel, well, you know that your high resistances, if you have a low resistance in parallel with a very high one, your high one doesn't really matter, right? You can just assume it's a small one. Well, here, if I'm taking these really high ones right here, and let's just say P5 is much larger than P3. Sorry, this is very messy, but this is P3. Well, we know this is going to be, this sort of FH is going to be approximately P3, because they're all in sort of parallel. And so that gives you sort of your lower bound for P3. Does that sort of make sense? So all of these poles are approximated by adding them up in series, right? And then the lower bound of FH is taken by taking these higher poles and sort of adding them in parallel. Does that sort of make sense? And so these poles, if you go back to what I said earlier, these poles are your coupling ones, your low frequency ones, and these are your high frequency ones, your shunting. Now this graph is pretty important because we can pretty much take all of our analysis and relate it to this graph. And so you don't have to sort of memorize things, you can just sort of intuit them. It's very powerful. Are there any questions so far about how I've gone about this? No? Okay. Great. Now, I did state earlier, I didn't actually state it, but for our open circuit time constants, it is understood that when you look at your high frequency models, the analysis does get a bit more difficult, at least for our hyper-pi models. And the reason for that is because we start doing things like, let me draw it here. We start getting, let me draw back here. I drew it here somewhere. No, I threw it away. That's not nice. I'll just redraw it. Okay, This is your C pi. This is your C mu. So when we're doing our open circuit time constants, C pi might be easy to analyze because this is with respect to, well, commonly ground. I'm taking a special case here, but usually it's commonly ground. C mu is not easy to analyze because it's between two different nodes. It would be much easier if we could break this down into a different network that connects that capacitor to ground. And so that's what Miller's theorem is for. Now, I could just sort of recite how Miller's theorem works, but, oh, I do not have much time. But, actually, no, I can probably just derive it very quickly.
I don't think so.
No, you don't think so? Just do the question? Maybe, that's probably right. All right. If I'm just going to skip the derivation, what I'll say, unfortunately, I'll just sort of just say, based on my notes, that C pi, or C mu, can be broken up into two things. You can break it down into C mu dash could be broken into C mu multiplied by 1 minus K, where K is going to be V2 on V1. I'm sorry, guys. I can't really show you guys how this actually happens. But if I had time, then I would show you how this was derived. And then your other C mu would be 1 on 1K. And then a lot of time, this would be between these two voltages. Now, K is usually pretty large, so C mu dash dash is usually equal to C mu. All right, that's enough for that. I should probably just do the example so that we can go on to the next part. So we're given, where is it? There we are. So we're given this circuit right here. Looks somewhat similar to assignment 1 maybe, but a bit simpler because you won't have that sort of time in the final to analyze a very complicated circuit. And so what the question asks is that you have to find the mid-band gain from R in and R out. And then given C1 and C2, given some values for them, you have to approximate FL. And we assume that CE1 and CE2 are very large. So what does that mean? CE1 is this capacitor here and this one there. We assume these to be very large. If you think back to my relation earlier, 1 on RC, if C is very large, then these poles are very small. So if I go back to this diagram here, these low circuit poles, these low frequency poles, oh my gosh, sorry. One of these, or these two of these, are going to be way to the left. So they don't matter. So you ignore them from the analysis. It makes analysis a lot easier. Okay. Now, I should probably just draw this circuit. I don't have the time to convince you that it's correct, but it is. I'll just copy it down very quickly from my notes. But I'm pretty much just using I'm getting this circuit here, and then I'm going to turn it into its equivalent circuit. So bear with me. Oh. I'm running out of space. That's not good. Alright, that's for you.
Just while Lith is writing, if you guys want access to the slides or also access to the docs that Josh had made, I'm chucking them on the stream
So just follow the link. It should be on the ELSOC drive.
Okay, that's the circuit. It's not very nice, but I just sort of have to quickly write it down. This is going to be, this has an RS there. This is going to be C1, this is going to be C pi, this is C pi. In any case, these are the values. Now I just probably just derive the answers for you guys. Now it asks, find R in and R out. So we're looking for the impedance through here. Well, if we disconnect this, we're not checking from the source because that's not actually part of our system. That's an input to the system. So we're actually looking from here. What this is that, oh my gosh. Okay, probably hurry up. This would be, it would be R1 parallel R2 parallel R pi 2. And that's from this circuit. So I don't have much time to explain why that is, but this one is in parallel with this, and it's parallel with the R pi resistor inside. So that'd be R in. Hold on 1 second. Parallel R pi 1. Now R out is going to be the resistance looking in from here, and we can already see that that's going to be RC2. There's also RO2, or the output resistance from the model, but we assume that to be very large, so to say. So we just say it's RC2. And that's the answer to that. I just sort of eyeballed the answer. So there you go. And then the next part was find C1 and find FL and FH. Okay, so I can probably state how you do this. So FL would be 1 on tau 1 plus 1 on tau 2. This is, and then you divide by 1 on 2 pi, sure. This one, tau 1, you would find from getting your, you would open circuit C pi and C mu. You would open circuit all of these, open circuit this one as well. And then you would short circuit a lot of these external capacitors like that. Let me use a different color. This one would be open circuited in any case. And then you just find the values, open circuit time constants from C1, and that's not C mu. I wrote that wrong. That's C2. This is C2. This is C mu. So you just find 1 on RC1 plus 1 on R2C2. Now we wouldn't find these values because they've said that these poles don't matter. They're very low. Sorry, I'm rushing through this, but bear with me. So that's how you find FL. If you wanted to do the question, the actual answer that I computed was about 3.1 hertz. It's pretty low, but it works out with LT Spice, so it works. Okay, and then FH. Quickly, this would be the open circuit time constants. RC plus there'll be 4 of them actually, wouldn't there? Because you've got RC pi. Sorry, maybe use blue. You have RC pi. You've got C pi, C mu, and you've got another C pi. You have another C mu here, and these are your intrinsic capacitors. So C pi 1, C mu 1, C pi 2, C mu 2. Now, what we also know is that when we do Miller's theorem, our C mu, right, when we break this down into something like this, these like right side capacitors become very, very, they become very, very small, and these ones become very large. So because these become very small and those become very large, we know that when pi is equal to 1 on RC, if C becomes very small, then the pole gets pushed right to the right, or a lot to the right. So then if we have a pole that's way on this side, well then it doesn't matter. So just sort of linking it back to the diagram that I made earlier. And so all you have to do is just find RCE, this one, and then this one. And then these ones don't matter. So this is how you would save time. Sorry, I should probably just give it to Jashin now. Sorry guys, that's all I've got time for. I'll probably make a video and then maybe put it up. Let's go through this more rigorously. But yeah. Alright, sorry.
All right, let's do feedback now. All right, let me get this. Okay, so what is feedback? Feedback is the process of just returning some of the output back into the input. The amount that we choose to return is denoted by beta or k in some texts. Okay, the closed loop gain is given by this equation, and if we find that beta A0 is significantly greater than 1, we get the closed loop gain basically independent of the transistor parameters. And this is very useful. Okay. So why do we use feedback? Gain becomes determined by passive components rather than varying with transistor parameters. So one example, we had that temperature example. IS is determined by thermal voltage. IB is determined by thermal voltage, like the equation we saw over there. And that first term, IS, is also dependent on temperature as well. So if we have our supply rails change as well, let's say, because we're not going to use the lab bench power supplies for all our circuits, right? We can use a battery. And if the voltage changed slightly on that, your parameters would also change. And feedback fixes that, okay? Here's a nice little meme. So if you wake up one day, your transistor says, no, I'm giving you beta 100 because it's too cold today. 120, can't do 100, but yeah. Well, the 4 topology is probably the most important part of this. So we got shunt, shunt, shunt series, series shunt, and series series. Note these little relations over here. Current voltage, current current. I'll explain why I've asked you to remember this in a little bit. Let me just get some notes up over here. Okay. Okay. Very nice. Actually, one little thing over here. Why do we use feedback? So, if we have an amplifier that gives a voltage as an output, it becomes a better voltage source. Okay? And I'll give this little example to show you why. With some intuition, not with just the maths. Okay? So, we have RS, the source resistance. We don't know what this resistance is. Okay? Let's assume it to be some fixed quantity for now. Okay, and we have the RL, the load resistance, okay? So there'd be a voltage divider across this, right? And if your load decreases with the resistance, there's gonna be a more even split. But negative feedback says, no, I'm not gonna let the voltage change. I'm gonna go back and I'm gonna feedback some back into the input. Our voltage stays the same. So our impedance actually improves. Depending on what you have over here, depends on your topology, of course, and whether you're outputting a voltage or a current. Okay, so what topology? I'm going to become an ant for this example. I'll draw this up for the viewers online, but if I was an ant and I'm at the input, okay, let me get this. Okay, I'm following along over here. What do I hit? Let's see, I can use this one. I'm following along on the input. What do I hit first? I hit my MOSFET first. So this means it's shunt, okay? This means it's series. And now I'm an ant and I'm coming in from the output, okay? I hit the feedback network first. So this is series. So this topology is shunt series. Let's move on. This example, okay? I'm an ant again. I'm coming in from the input, and I see the feedback first. This is shunt. Okay, now I'm going in from the output over here, it's series. Okay, sorry, the last one was series shunt. I just said it wrong. Yeah, okay, so here's a little formula, the feedback formula, and this will help you solve these kinds of tricky questions. These are pretty big questions. Okay, identify what topology you have. Okay, then we're going to find K or beta, the feedback factor. This part's a little different. The lectures you might have seen transistor parameters not transistor parameters, but G parameters, Z parameters being pulled out. I'm going to show a little bit of a different way. I think the way that's been explained in the lectures is sufficient. I'm going to show a little different perspective on this. Okay? Then we're going to find the open loop gain and then the closed loop gain, and the rest is pretty simple. Okay, so let's find the feedback factor from example 1. We can screenshot this. Actually, I can draw on this one. Okay, so I'm going to short C5 for this. So we're going to replace this with a short. Okay. This one's a little hard to see. So you've got this 10K over here, got this 10K right here, and this 0.2K. So we have this current mirror. We also have the C4. We're going to short that as well. Okay. So it's essentially like this. And then that node, this node over here is X right over there, okay? That's a simple voltage divider. So we have 200 over 10K plus 200 times V out. And I don't have the exact value for that. That's 19.61 times 10 to the negative 3. Does that make sense? See, is that voltage divider hard to see, or is like, do you want me to redraw the circuit so it's a bit? Okay, let's move on. Okay, next question. We're gonna find beta again. So let's scroll back. This one's a little bit harder to spot, but it's a current divider. So we're just gonna get beta equals to minus RE2 for RE2 plus RF. And I've obviously shorted CF in this case. Okay? Okay, we got that. Now, I did mention that I'd suggest a different method of opening the loop than's been suggested in the lectures. So, what we're going to do, we're going to create a copy of the feedback network on both input and output. Okay, it might be a bit hard to see now, but you'll have a floating node. And, well, what do we do with a floating node? Okay, so if we're summing the voltage, we ground this floating node. Otherwise, we'll just leave it open. If we're sampling current, we'll ground it. Otherwise, we'll leave it open. Okay, draw the open loop circuit for example 1. I don't think I'm gonna get away with using the image over there. So I'm just gonna have to do that. So I'll omit the current mirror for now, and I'll just draw the rest of the circuit. Whatever's on this side of the circuit doesn't matter, sort of. So we can just 200, and what I'll do, I'll refer back to the circuit diagram so I can give a bit of a clearer explanation to what I'm doing. Okay, so what I'll do is, this is shorted, but I'll move this out a little bit, and then the 10K from here, it's going to hop along over here, and it'll be open around there. Okay? Okay, so 200, 10K. Here's our floating node. Okay? And then I'm just going to draw the rest of the circuit in over here. Oh no, where did I? Is it? Oh, okay, you guys didn't see that, but I accidentally exited the document. 10K, yeah. We're short on time. This is going to be me speed running drawing circuits for the next 10 minutes. Okay, so I'm going to copy the feedback over here again. But now this is floating. So what did we say we're going to do? We're going to ground this node and we're going to leave this open. Okay? And okay, so I did say I wanted there to be some intuition behind this. So, because writing this, still a bit. So, if we think about it, we're sampling a voltage, so we want our resistance to be high, right? So we don't load the other circuit. So we'll leave this open. We want to sum a voltage over here, because input voltage right next to this. So we want to act like a voltage source. So we'll reduce the resistance by grounding it. And that's sort of one way you can think about it to arrive at this instead of using the parameters. I think try both methods and see which one works for you. If you like thinking about it like this, I reckon go for it. You arrive at the same result. You will still get, I don't remember the exact parameter, whatever it's called. You still get the exact same circuit though. So that's the important part. Okay, example 2. Let's see if I remember example 2 circuit. Okay. Two. Oh yeah, that's fine there. Okay. And then I'm going to add on our RF over here. I'll show the circuit again after so it's a bit more clear. Okay, then we have and then our open node is here. And oh, I already revealed the answer, but that was supposed to be grounded. So open node there and open node there. We'll just ground both of these. Okay, we've opened the loop. Now what we'll do, we'll finish the rest of example 1 because example 1's a 2024 exam question. 8 minutes. Let's see how far we get. Okay. So we're going to try and find the closed loop gain. I'll show this circuit again. Okay, so this is a pretty big circuit and it looks really complicated. How am I going to go about this in a way that isn't going to overwhelm me? Well, the first thing I see, this little circuit over here. Does anyone, well, I've already said it. It's a current mirror. So I'm going to find the current in the current mirror, and I'm just going to say that it's a current source over here. So I eliminate that. Okay. I'll leave this floating for now. It won't affect our calculations. One thing to note that the ratios of the W to L of these are both the same. Assignment 2, they're not, so you might have to look at how your current changes. But yeah, this is minus 5 volts. Okay, so quick little KVL will get us 10 minus VGS for this MOSFET over here, over 8.8K. Now I'm going to use a current equation, Kn W over L VGS minus VT, which is 0.6. Oh, I'll move this over here so it's a bit easier to see. VT I'll just sub this straight in. 6 squared. A little trick you can use here, we'll turn this into x, okay? And I'll turn this into alpha. So it's just two constants, you can call them whatever you want. 9.4 minus x. Now I don't have to expand this quadratic out. Okay? So you end up getting the quadratic plus x. That's the correct quadratic, I'm pretty sure. I'm not going to solve that on the calculator right over here. So I'll just give you x is equal to 363. Okay, and then this gives us VGS is equal to, well, from over here we can already eliminate one of these. That's this one, because we want our MOSFET in saturation, so we can't have a VGS minus VT less than 0. Okay? So we move on. We redraw the circuit now, except with the current mirror is now gone. Actually, we need to get ID from here first. Let's go back really quick. So we've got VGS. Want to find ID. ID, if you remember from this equation, right over here, that's just some substitution and bashing the calculator, and you'll get, sorry, not equals, you'll get about 1 milliamp. A certain approximation's been used over here. I can't tell you which. Okay, I'm just going to redraw the circuit now. Oops, there's a resistor over here. Okay, and then okay, so what we'll do over here, there's some working out that I kind of want to skip in the interest of finishing the question, but I can essentially find the Thevenin equivalent of whatever's on this side and then replace it with that. So I get my, it's a bit more simpler. Okay, quickly do that. Actually, I'll leave that. We'll leave that and we'll just go like it was before. Okay, the 1 mega ohm resistor. $197 ohms, and then we have that current source over here, so I'm just going to call that ID1. Okay. Now, what that current source sets is the ID for this, the IE for this. Okay. So we have ID2 is equal to 1 milliamp. IE2, no, sorry, that's IE, is equal to 1 milliamp. Okay, so we get IC is about beta on beta plus 1 times IE. So we can say from here that IC is about 1 milliamp. Okay, this lets us find everything we need. What parameters do we need? Well, we've got IC. We need GM1 for the transistor up the top. We need GM2 of the MOSFET, and we're set to find everything. So GM2 is equal to IC over VT, which is equal to 38.46. Okay, GM1, 2ID is equal to, Okay, very nice. So we've got everything we need now, all the parameters that we need to find the gain of this. Okay? Now, let me go back. I'll copy this circuit, but I'll solve this a little differently. I'm not going to use a single small signal model for this. I'm just going to solve this all by pure intuition, all from the equations that I derived in that document and the ones that I tried to quickly derive over here. Vy, V0 dashed.
Sorry? I have a lecture here, yeah.
Oh, yeah, okay.
Sorry, 6 o'clock.
Yeah, okay, so I'll quickly just state the gains for all of these. You get about 25.74 over here. No, that's over here. Minus 0.065. This is an inverting amplifier, so you get minus 10. Over here. Total gain's about 17.64. That makes your closed loop gain about 13. Yeah, I'm sorry we couldn't complete this question. We've run out of time, unfortunately. Yeah.
Thank you all for coming.
Thanks so much for coming, everyone. I had to speed run that, bro, and I still couldn't get it. Oh,
No, but that was good. That was good. You got to the important points, like the tricks, and all that stuff.
Yeah.
Whose is this?
That's not mine. Are you gonna stop the stream?
Yeah, I'll stop the stream.
Yeah.
What day is the exam?
Not remember, 19th?
Oh, okay. You got